our project is about simulating the behavior of a designed 3D model under various recovery methods. This is going to be our outline for this project. To start off, the main aim of reservoir characterization is to build a geological model that honors all available data that can be used to estimate porosity, permeability, and fluid distribution across a certain field. In order to create that model, we need to use a simulator which is reliable, quick, and precise. Fortunately, Eclipse software has all those qualities, which allowed it to be the industry reference for reservoir simulation for over 25 years now. Using Eclipse, we will simulate a small reservoir comprised of 87,000 stock tank barrels of dead oil, which is known to be highly viscous, therefore very hard to produce. Then we will apply several recovery methods in an attempt to find the best one to recover the dead oil present in our reservoir.
Lorentz curve is a method used to estimate the heterogeneity of a certain reservoir. It is an essential method to construct the model in the Eclipse software. The scatter of permeability values is used to evaluate reservoir heterogeneity. So in this method, we'll be evaluating the permeability measurement for certain layers and calculating Lorentz coefficient after applying the corresponding method. We are aiming to have a heterogeneous reservoir with a Lorentz coefficient of 0.6. So we will enter all the data into an Excel sheet and replace all the formulas that will allow us to create a Lorentz method. After we estimate all the data, we may now plot a graph of the variation of transmissivity as a function of storativity. The Lorentz curve is frequently accompanied by a diagonal line that passes through the origin 0, 0 and reach point 1, 1 as shown in this figure. Once the graph has been constructed, it's now time to find the area between the curve and the diagonal. This is done by dissecting the area under the curve into multiple triangles and rectangles. After that, the Lorentz coefficient is equal to 2 multiplied by the area between curve and diagonal.
To create a base model using Eclipse, the input file should incorporate the following sections. To start off, run spec is the first section of an Eclipse data input file. The main keyword that comprises this section up is diamonds. This keyword defines the basic size of the simulation grid. It is followed by 3 integers specifying the number of cells in the X, Y, and Z directions respectively. In this scenario, the number of grid blocks in each direction was set as follows: 50 grid blocks in the X direction, 50 grid blocks as well in the Y direction, and finally 27 grid blocks in the Z direction. Now, moving on to the grid section, it is the second section of an Eclipse data input file. It determines the basic geometry of the simulation grid and various rock properties. The essential keywords used in this section are dx, dy, dz. It represents the grid block sizes in X, Y, and Z directions. It is illustrated as total number of cells multiplied by the size or thickness of each cell in each of the X, Y, and Z directions. We also have the perm X, perm Y, and perm Z keyword. It is used to represent the grid blocks permeabilities in X, Y, and Z directions. And since the reservoir is assumed to be homogeneous isotropic, so the permeability in all directions is uniform, meaning that perm X is equal to perm Y is equal to perm Z. We also have the equals keyword, which is used to replace or assign the value of a property for a box of cells within the grid. Now moving on to the props section, which is the third section of an Eclipse data input file. It contains pressure and saturation dependent properties of the reservoir fluids and rocks. It is comprised of a set of keywords, mainly which are PVDO. This keyword represents the PVT properties of a dead oil. And since the dead oil is chosen in our case because the only active phases present in our model are water and oil, hence there is neither free gas nor solution gas or dissolved gas present inside the oil. We also have the PVTW, which shows the PVT properties of water. And finally, we have the rock, which expresses the rock properties, in which it consists of 2 major components: the reference pressure, P reference, set as 4,500 psia, and the rock compressibility, which is set as 4 exponential 0.6. Now, moving on to the solution section, which is the fourth section of an eclipse input data file. It contains sufficient data to define the initial state, including pressure, saturations, compositions of every grid block in the reservoir. This section involves a keyword, which is equal. This keyword specifies the following terms: the oil-water contact depth, which is set as 8054 feet, and the capillary pressure, which is set as 0 psi. We also have the summary section, which is the fifth section of an eclipse input data file, which specifies a number of variables that are to be written to summary files after each time step of the simulation. In other words, it details the expected outputs after the simulation is run. To obtain a single producer well, all the previously detailed sections, including the run-spec grid, prop, solution, and summary, will be part of the input data file to Eclipse, but with one additional section, which is the schedule section. This section is the final section in an Eclipse input data file. It specifies the operations to be simulated, including production and injection controls and constraints, and the times at which output reports are required. Major keywords in this section are well specifications, which introduces a new well, defining its name, the position of the wellhead, its bottom hole reference depth, and other specification data. We also have the completion data, which specifies the position and properties of one or more well completions, and so on. Once the simulation has been run, the following output was yielded. The first graph represents the field pressure as a function of time. The second graph representing the field oil production in total as a function of time. The third graph representing the field oil recovery efficiency as a function of time. And the fourth and final graph representing the field water production in total as a function of time.
Water flooding is a technique used to increase the recovery factor of oil-bearing reservoir. It's performed to maintain reservoir pressure and recovery from 5 to 35% of the remaining oil in place. Most common spot patterns are 2, 3, 4, 5, 7, and 9. In our case, we will be using the 5-spot pattern. There are many factors that affect the outcome of water flooding, such as porosity, matrix permeability, wettability, fluid properties, contact angle, rock properties, and fracture intensity. In the figure below, we can see the effect of 5-spot pattern on our reservoir. In the graphs below, we can see the total cumulative oil produced from well versus time, oil production rate versus time, recovery factor versus time, and cumulative water production versus time.
Okay, so moving on to the polymer flooding, it is one method of the chemical enhanced oil recoveries in which long chains of organic molecules, which are known as polymers, are added into the displacing fluid, which is water, and injected into the reservoir. Once the polymer is injected into the water, its viscosity will increase, and hence the relative permeability of water with respect to the oil will decrease, and hence also its relative mobility ratio. By that, we will have a more efficient sweeping of the oil and a better production case. The polymer flooding is used in several cases. One of these cases are the high permeability regions, because these high permeability regions attenuate the efficiency of the water flooding by redirecting its flow. Here we can see the result of the reservoir under the action of the polymer flooding, where it has a more saturated water sweepage. We can see the cumulative oil production in the upper left figure. It has increased. Also, we can see the water cumulative production in the upper right figure, and we can notice how it decreased slightly. In the lower left figure, we can see the efficiency of of the production, which has also increased under the action of the polymer flooding. And most important, the concentration of the polymer at the producer well is shown in the lower right image, and hence we can detect the propagation of the polymer from this graph.
Comparison between the single producer and the 5-spot pattern water flooding. We can see that field oil production total, field oil recovery and efficiency, and field water production total have increased drastically. This indicates that the 5-spot pattern water flooding has enhanced the overall performance of the reservoir, but at the cost of having an elevated water cut condition. Hence, we can say that the 5-spot pattern is more beneficial. Comparison between the 5-spot pattern water flooding and 5-spot pattern polymer flooding. Field oil production total is noticed to have increased in the 5-spot pattern polymer flooding, but in very limited manner. In other words, polymer flooding field oil production total is 352 more barrels of oil than the conventional 5-spot pattern. Similarly, polymer flooding has yielded a recovery factor greater than the witnessed in the conventional 5-spot pattern. However, the cumulative producer water is less than the produced in the 5-spot pattern, which indicates that the polymer addition has increased the water cuts. Therefore, we can say that the 5-spot pattern polymer flooding is better than a conventional 5-spot pattern water flooding, although the difference is set at a very small scale. It is also better than the single producer scenario.
So as a conclusion, and after the comparison of the 3 recovery methods, the 5-spot polymer flooding was found to yield the optimal results. Normally, we would consider the results yielded to be significantly low. However, with such a small reservoir composed of dead oil and the large uncertainties in the SWOF tables, the numbers we saw are considered to be perfect. Now let's move on to the eclipse demonstration.
So now we will be seeing some codes, typically around the polymer flooding. So concerning the PLY-VISC, which is a polymer viscosity, it indicates that for a 0 concentration of the polymer, we have 1 times the viscosity for the water. For 1 concentration of the polymer, we have 5 times the viscosity of water. Concerning the PLY-ADS, which indicates the polymer adsorption, it is 0 for any concentration in the water. The PLY-ROC indicates that it indicates some information about the DAD for the residual resistance factor, the mean density, and so on. The PLY-MAX indicates that indicates the maximum concentration to be used for the polymer, which is 1, and the maximum concentration of salt in the water. Here we have 0, so it is a salt-free water. The polymer mixing parameter is 1, which indicates that we have used the Todd's Longstaff records in order to use it as a mixing parameter for the viscosity calculation. We will move on to see some simulation in 3D. Here we can see a single producer case. We can notice slightly how the oil-water contact is moving slightly upward in the single producer case. In the polymer flooding case, which we have a 5-spot pattern, we can notice how the sweepage of the oil is taking place. And as we said, it is taking place in a more water-saturated manner than an ordinary 5-spot pattern. By this, we can say that we have ended up our presentation, and we hope that you enjoyed it. Thank you.